All right. Hello, everyone. This is a CHL lesson for the week of May 24th. And today we are going to be talking about unit analysis. Or maybe you can call it dimensional analysis. I don't know, whatever you want to call it. And so what we're going to learn how to do is how to figure out the units of random constants in equations, for example, how to guess equations, and some other really useful things and kind of fun things too. So the first thing I wanted to talk about is that every physical quantity has units of the form kilograms to the x power, meters to the y power, seconds to the z power, and coulombs to the, I'll say, a power. Okay? So basically any unit can be written in the form of a product of mass, length, time, and charge to different powers. Okay? All right, so I will write this because we're trying to talk about units in general. Okay, I will write this as m to the x, where m represents just any unit of mass, L to the y, where L represents any unit of distance, T to the z, where T represents any unit of charge, okay, and C and Q to the A, where Q represents any unit of electric charge, okay? So the units of any quantity has to be of this form, all right? So for example, what if, let's determine some units here. What are the units of force? And by the way, when we write the units in this way, I'm going to say that these are the fundamental units. Okay. So anyways, if we think about what are the fundamental units of force, okay, what I want to do is I want to think of an equation that has force in it. The first equation that comes to mind is Newton's second law, which says that net force equals ma. So that means that the units of force are going to be equal to the units of mass times the units of acceleration. Now, mass is measured in a unit of mass, and then acceleration is meters per second squared, right? So acceleration is a length per time squared, meters per second squared. So its fundamental units are length per time squared. So I could write the units of force as m to the 1, L to the 1, T to the negative 2, and Q to the 0. So those are the fundamental units of force. Now, of course, if I chose to write this in SI units, then this would be, when I say SI, I mean metric. In SI units, SI stands for Système International. That would mean that the units of force are kilogram meters per second squared. All right, and this, of course, has the name newtons. So 1 kilogram meter per second squared is defined as 1 newton. I don't know, if we were to use imperial units, all right, if we were to use imperial units, we would have, I don't know, we could have units of force. The mass is maybe measured in pounds. So maybe pound. Length is measured in inches. Pound inches per minute squared. I don't know, something like that. So we can come up with a bunch of different units of force depending on our system of units. Okay, but all units of force are going to be a mass times a length divided by a time squared. Okay, let's do the same thing for maybe energy. What are the fundamental units of energy? Well, energy is, we got to think, if we wanted to figure out the fundamental units of energy, let's think of an equation that has energy in it. One that I'm thinking of is kinetic energy. Kinetic energy is an energy. So the units of energy are going to be the units of 1/2 mv squared, right? Which is just going to be the units of 1/2 times the units of mass times the units of speed squared. Now, 1/2 is just a number, it's unitless, okay, so its units are nothing. M, that's m to the 1, and then we have speed, which is length per time, but that is squared. So our fundamental units of energy are m to the 1, L to the 2, T to the -2. Okay, we could arrive at this a different way. For example, we could say that work is a form of energy, and work, so the units of energy and the units of work are the same. Work is force times displacement. Okay, the units of force I just figured out from this previous example are m to the 1, L to the 1, T to the -2. Okay, and the units of displacement are L. So I have L to the 1 times L to the 1. So I have m to the 1, L to the 2, T to the -2, once again. Okay, so this is how you find the fundamental units of some quantities. A lot of times you have like an equation, all right, where there's some random constant in the equation, okay? So how do we find the units of a constant in an equation? So finding the units of a constant in an equation. So let's say, for example, suppose that the drag force So the drag force is a constant times the speed squared. Okay? So then what I want to do is, and I'm trying to figure out what are the units of this constant c. I already know what the units of force are. I already know what the units of speed are, but what I really want to know is what are the units of this random constant that showed up in this equation. So what I want to do is I want to do a units of that equation. So I'm just going to replace every variable with units of that variable, because equations have to match in terms of their units. Okay? So units on the left-hand side have to equal units on the right-hand side. Now the units of force, the fundamental units of force are mass times distance divided by time squared. MLT to the minus 2. We proved that right here. And then on the right-hand side, I have units of c. And then I have units of speed squared, so that's going to be L over T squared. Okay? So if I then simplify this equation a little bit, so I have a t squared on the denominator that I'm going to multiply over, and it's going to cancel out this t squared. And then I have an L squared that I'm going to divide over, and that's going to cancel that out. So I get that the units of c are m to the 1, L to the negative 1. So for example, if we were talking SI units, this would be kilograms per meter. Okay? Or if we were talking, I don't know, imperial units, it could be pounds per inch or something like that. Okay? So the fundamental units, no matter whether we're using metric or imperial or what have you, the unit of C is always going to be of the form a unit of mass divided by a unit of length. Okay? So this is how you find the units of a constant in an equation. Another example would be with gravity. So we have this equation, F equals big G m1 m2 over r squared. So this equation has a random constant in it, which is big G. So what if we want to know what are the fundamental units of big G? Well, I would replace every variable with its units. So I have units of F equals units of G times units of M1 times units of M2 divided by R units of R squared. Okay? So on the on the left hand side, we have again a force, so that's going to be MLT to the minus 2. On the right hand side, I have units of G, and then I have units of M1, which is just going to be mass, and then I have another unit of mass, right? So that's going to be m squared. And then r is a measure of distance. So I have, and it's in the denominator and it's squared, so I have L to the negative 2. So you can see that I can solve for the units of G. So if I divide both sides by m squared, I get m to the minus 1. If I divide both sides by L to the negative 2, on the left-hand side I get L to the third, and then I have T to the minus 2. So these are the fundamental units of the gravitational constant. Mass to the negative first, length to the third, and t to the minus 2. So that we're going to use that. There are some other fundamental constants of nature that we should probably know the units of. There is h, which is Planck's constant. And Planck's constant shows up in quantum mechanics all the time. It's like, so big G is like the main gravity constant in the universe. H is the main quantum mechanics constant in the universe. And so its value is 6.6 times 10 to the minus 34 joule seconds. Okay. And the fundamental units of Planck's constant are, it is kilogram, well, it's going to be mass times a length squared times a time to the negative 1. Okay, so if you work it out, joule times a second. We saw here that a joule is this. So if I multiply, see how it's measured in joule seconds. So if I take a joule and I multiply it by a factor of t, I get this. Okay? So those are the fundamental units of h. Okay? And then we also have the speed of light, c, which is speed of light. And it is equal to 3 times 10 to the 8th meters per second. The fundamental units of c, it's a speed, so that has fundamental units of L, t to the minus 1. Okay? So did you know that we can combine G, H, and C to make something that has units of length? Okay, so that's what we're going to do for an example. Okay, so we can combine big G, H, and C in such a way that they have units of length. Okay, so watch. Here's how we do it. So we're going to say, all right, let's suppose that something has units of length. It's G to the X power, H to the Y power, and C to the Z power. Okay? And we want the units of this to have units of length, L to the 1. And so we are going to choose the powers, X, Y, and Z, that make this equal to L equal to 1, that have units of length. We could also think about this as M to the 0, L to the 1, T to the 0, right? Because anything to the 0 power is 1. Okay, so if I have G to the X power, well, let's look at the units of G. M to the 1, L to the 3, T to the minus 2. So that means that the units of G to the X power are going to be M to the negative X, okay, L to the 3X, and T to the negative 2X. Okay, so those are the fundamental units of G to the X. Okay, so all I did was I took this and I raised it to the xth power. Okay? Maybe I should zoom in one more. Okay. Then I have the units of h to the y. Well, h has fundamental units of ml squared t to the minus 1. So I have m to the y, l to the 2y, and t to the minus y. So that is the units of h to the yth power. Okay. So again, I just took this expression right here and I raised it to the yth power. So I have m to the y, l to the 2y, t to the minus y. And then lastly, we have speed of light to the zth power. So that's going to be length to the z times time to the negative z. All right? Because it's length per time to the zth power. All right? So, and that has to, so the units have to match. Okay? So I'm going to combine all these first of all. So I have m to the y minus x. Okay? I have L to the 3x plus 2y plus z. So that's coming from L to the 3x times L to the 2y times L to the z. And then I have t to the minus 2x minus y minus z. And all of this has to have the units of m to the 0, l to the 1, t to the 0. Okay? So this actually gives us a system of equations. Okay? Because the powers have to match. The power of mass on the left-hand side has to match the power of mass on the right-hand side in order for the units to match on both sides of this equation. Okay? So we have y minus x equals 0. That comes from matching the powers of m. We have 3x plus 2y plus z equals 1. And then we have minus 2x minus y minus z equals 0. Okay? So this top equation, it obviously says x equals y. So then I can rewrite the bottom two equations as 5x, because x equals y, right? So 2x plus 2x, or 3x plus 2x plus z equals 1. And then here I have minus 2x minus y, which is the same thing as x. So I have minus 3x minus z equals 0. Now if I add those two equations, I get z minus z, 1 plus 0, and then 5x minus 3x, so 2x equals 1, which means that x equals 1/2. Okay. All right. And then we also have that x equals y. So that means that y equals 1/2. And then from this equation, taking this equation, that one says that negative 3x equals z. So that means that z equals minus 3/2. Okay? So this has solved this equation. So that means that g to the 1/2, h to the 1/2, c to the minus 3/2 has units of length. And this length has a special name. It is called the Planck length. L sub p. Okay? And this is the unique length that you can build out of these fundamental constants, okay, of nature. So it must be an important length. Something special has to happen at this length scale. Okay, so some scientists believe that increments of length smaller than the Planck length don't really even make sense. So it's kind of like the smallest, now we don't know because we can't measure anything this small, as we'll calculate in a second. But, we can't access distances that are this small. But we know that this distance must be an important distance in the universe. Okay, the characteristics of the universe change when we approach the Planck length. Okay, so anyways, let me calculate the Planck length. So G is 6.7 times 10 to the negative 11, the 1/2 power. Planck's constant is 6.6 times 10 to the minus 34 to the 1/2 power. And then C is 3 times 10 to the 8th to the minus 3/2 power. Okay? So this has units of meters. So let's calculate it. So this is about 4 times 10 to the minus 35 meters. That is the Planck length. So we think that possibly that is the smallest distance scale in the universe. And it's based on the fact that this is the unique length that you can build out of these fundamental constants of nature. Like, these are the most fundamental constants that we have in nature. Okay, so there's also a Planck mass, there's a Planck energy, there's a Planck time, etc. And those are defined in the obvious way. So the Planck energy, for example, is the unique way that you can combine all these to get something with units of energy. All right. So we kind of have the basics of unit analysis. So now I want to move on to guessing equations. Okay. So to do that, let's consider a problem that we have solved before. Okay. So let's say a car starts with speed v. Okay. It decelerates at rate a. Okay. How far does the car travel while rolling to a stop? How far does the car travel while rolling to a stop? Okay, so if we were going to do this with kinematics, we have this equation. v final squared equals v initial squared plus 2a delta x. Okay. We know that v final is 0. V initial is v. The acceleration is negative a because it's decelerating at rate a, so negative 2a delta x. And so what we get is delta x equals v squared over 2a. All right? But what if I had no idea about kinematics equations? You could actually make a pretty good guess. Okay? Because I know how far it's going to travel depends on the velocity and it depends on the acceleration. Okay? So let's assume that delta x has the form k times v to the a, let's say v to the m, we'll say v to the m, times a to the n. All right? So let's assume that this is the form, where k is some unitless constant. Okay? And m and n are powers. And we are going to choose m and n so that the right-hand side and the left-hand side have the same units. Okay? So if I do the units of this equation, the left-hand side has units of length. The right-hand side, k is a unitless constant, so the units of the right-hand side is just determined by this. V to the m has units of L to the m over T to the m. Okay? And then A to the n has units of L to the, it's meters per second squared, so L to the n divided by T to the 2n, because it's meters per second squared. Okay? So what we can see here is that m times, or if I multiply out the powers of L, I get L to the m plus n on the right-hand side. Okay? So that means, and this is L to the 1. So matching powers of L on either side tells us that m plus n has to equal 1. And then we could also think about this as divided by t to the 0 power. So that means that m plus 2n has to equal 0. All right? So if I subtract these two equations, so this top equation is matching powers of L, the bottom is matching powers of T. Okay? And so subtracting them, I get minus n equals 1, which means that n equals negative 1. And then that means that m equals 2. So based on just purely unit analysis, I get that delta x is a constant times v to the m, so v squared, times a to the n, where n is negative 1. So we get over a. So you can see that combining velocity and acceleration, there's only one way to combine them so that they have units of distance. So the equation has to take this form. Okay? So in a sense, we didn't need to know physics to figure out this equation. In fact, all the physics does is it tells us that the constant k is equal to 1/2. Okay? But other than that, the equation had to have this form because that was the only way to combine speed and velocity, speed and acceleration in such a way as to have units of distance, okay? And we wanted to calculate distance. So there's only one possible way that those variables can be combined. So this is the way that you can guess equations, all right? Let me give you another example. There is something called a gravity wave. A gravity wave is a wave powered by, or I should say, a wave across the surface of a fluid powered by gravity. Okay, so in other words, if you have a hump of fluid, gravity pushes that hump down to try and make the ocean flat, and that makes the wave travel. Okay, we know a couple of things. We know that the speed of a gravity wave depends on the acceleration due to gravity. We know it depends on the density of the fluid. All right. And we know it depends on the wavelength of the wave. So these are the three things that the speed of a gravity wave depends on. And if we didn't know that, we could kind of guess that these are the important things that determine the speed of a wave. All right. So now let's assume, okay, that the speed of a gravity wave is equal to a unitless constant times g to the x, rho to the y, and lambda to the z. And we're going to choose x, y, and z such that the units on the left-hand side match the units on the right-hand side. Okay, so taking units of on both sides, I have units of speed are length per time. K is unitless. G has units of meters per second squared. Okay, density has units of mass per volume, so m times L to the minus 3. So we have that to the y. And then wavelength has units of length, so we have L to the zth power. Okay, so I'm going to match powers of L on both sides. So on the right-hand side, I have L to the 1. Or sorry, on the left-hand side, I have L to the 1. On the right-hand side, I have L to the x plus L to the minus 3y, and then times L to the z. All right, so that's matching powers of L. Matching powers of M. Here I have m to the 0th power. Okay, so on the left-hand side I have 0, and on the right-hand side I have m to the yth power. So that means that y equals 0. And then on the powers of t, on the left-hand side I have t to the negative 1. On the right-hand side I have t to the negative 2x. And that's it. Okay. So this bottom equation says that x equals 1/2. This, of course, says y equals 0. And then this equation says we have 1 equals 1/2 minus 0 plus z. All right. So that says that z equals 1/2. So z equals 1/2, x equals 1/2, and y equals 0. So the speed of a gravity wave, so this is like an ocean wave, is equal to a dimensionless constant times g to the 1/2 times lambda to the 1/2, and then times rho to the 0th power, so I'm not even going to include it. Okay? In this case, the actual equation is, so if we were to do a bunch of physics, we would find that k equals 1 in reality. Okay? And so the lesson is that, the lesson from that is oftentimes the constant has a size close to 1. Okay? And I say that in the sense of a Fermi problem. Like, you know, it's not going to be 100 or 1/100th. Usually it's, you know, a reasonably sized number that's around 1. Okay? We're going to do one more example. And this has to do with what is the size of an atom. And in particular, what is the size of the hydrogen atom? Okay. Now, it depends on the electric charge. So this is the fundamental electric charge, which is also the charge of an electron, the magnitude of the charge of an electron. It depends on the Coulomb constant. Hydrogen atoms are fundamentally quantum mechanical, and so anytime something is quantum mechanical, it's going to depend on Planck's constant, and it also depends on the mass of the electron. Okay. So these are the important things that determine the size of the hydrogen atom. Now, why doesn't the mass of the proton matter? Well, that's because the proton is basically so much heavier than the electron that the proton is fixed, and then the electron pretty much just moves around a stationary proton in the center. So the mass of the proton, other than the fact that it's big, is not very important. Okay, we already talked about how the fundamental units of H are m L squared T to the minus 1. The fundamental units of the mass of the electron are m, because it's a mass. The fundamental units of the electron charge are Q. And then the fundamental units of K, you can work it out yourself. It is, I wrote this down somewhere, it's going to be m let's see, m L to the third T to the minus 2. I'm just double checking in my head that I'm doing this correctly. Charge to the minus 2. Okay. Yeah. Okay. So the size. So this is the Coulomb constant, by the way. So this is that 9 times 10 to the 9th. So what we're going to do is we're going to combine e to the a power, k to the b power, h to the c power, m to the d power times a constant, which I'm going to call big A. And that is equal to the size of the hydrogen atom. Okay? So I'm going to choose A, B, C, and D. A is a unitless constant that is most of the time approximately 1. So I'm going to choose A, B, C, and D so that the units on the right-hand side match the units on the left-hand side. Units on the left-hand side are L to the 1, M to the 0, T to the 0, Q to the 0. Okay? The units on the right-hand side are Q to the A from that. Okay? And then K to the B power is going to be M L cubed T to the minus 2 Q to the minus 2 to the B. All right. Then I have H, which is M L squared T to the minus 1 to the C power, and then M to the D power. All right, so now I have to match the powers, okay? So powers of L. I have L to the 3B plus 2C on the right-hand side. I have M to the B plus C plus D on the right-hand side. I have T to the minus 2B minus C on the right-hand side. And then I have Q to the A minus 2B. All right. So now matching those powers, I have 1 equals 3B plus 2C, 0 equals B plus C plus D, 0 equals negative 2B minus C, and then 0 equals A minus 2B. All right. All right. So what I'm going to do is I'm going to take this equation. This equation says that C equals negative 2B. All right. So that means I can plug that in here, and I have 1 equals 3B minus minus 4B. So that says that B equals negative 1. Now, if I know B equals negative 1, then this equation says that A equals negative 2. All right. And then this equation says that B equals negative 1, so that says C equals 2. And then this equation says that 0 equals B plus, which is negative 1, plus C, which is 2, plus D. So that means that D equals negative 1. So the size of the hydrogen atom is going to be a constant times e to the negative 2, Coulomb constant to the B, negative 1, Planck's constant squared, and mass to the d power, so m to the minus 1. All right? And so we could use this if we assume that A is approximately 1, we could literally guess the size of the hydrogen atom. And if you do this, you'll find that it is about 10 to the minus 10 meters in size. And that is the actual size of the hydrogen atom. So it's crazy. It's like you can literally just, if you know what a physical quantity depends on, you can think about how do these variables have to be related to each other in order to get something that has the same units as, or what is the way that you can combine these variables so that they have the units of the thing that you're trying to measure. And you can use this to guess the forms of equations. Okay, it's really cool. It's a really useful skill.